Other coders. This lesson is about memory and how the memory is arranged in Java, to be exact. We'll also talk about the garbage collector, and we'll also touch on the object lifecycle, how its life begins, how it ends, and what makes it happy in between. Please make sure you give this video an emperor's thumbs up, toll the bell, and subscribe. So let's crack on with it. In good old languages like C and C++, the allocation of memory for objects, for example, occurs explicitly, and Java is not too much different in this case, but the release of memory can be a tedious and error-prone process, leading to unpleasant situations when, for example, an object won't release the allocated memory, or on contrary, releases it too early, while still requiring it. The first case scenario can cause the so-called memory leaks that can lead to the performance issues. The program slows down and then crashes completely. In the second case scenario, the program gains access to the so-called invalid memory. This can lead to unimaginable and unpredictable consequences. The solution might sound simple. When you've finished with the object, let it go, that's it. However, in reality, it's not as simple and straightforward as you might think. There could be situations when two different parts of the very same program use the very same object, or the architecture of the program itself is not so good or whatnot. So the creators of Java have wisely decided not to rely on the coder's ability to manage the program's memory and came up with something called garbage collector, a kind of scavenger that picks up objects not used by parts of the program and releases their souls. Memory. The Jvm divides memory into stack and heap for application optimization. Whenever we declare new variables or objects, call a new method, or declare a string or whatnot, the Jvm assigns free memory for these from stack, memory, or heap space. Let's have a look at them in more detail. Heap. Used to store objects and classes. New objects are always created on the heap, but references to them are stored in another area of memory, the stack. All objects on the heap are globally accessible, which means they can be accessed from anywhere in the application. The heap is divided into several smaller parts called generations. Young generation is the area where newly created objects are stored. Old or tenured generation is the area that stores long-lived objects. Prior to Java 8, there was another area, permanent generation, which contained meta information about classes, methods, static variables, but after the advent of Java 8, it was decided to store this information separately of the heap, namely in the meta space, which is dynamically sized, and at runtime it can expand to the size of the Jvm memory itself. So, key features of the heap. When this region of memory is full, Java throws java.lang.out of memory error. Access to the heap is slower than access to the stack memory. Garbage collector operates here and utilizes unused objects. The heap, unlike the stack, is not thread safe because any thread can access it. Now about Jvm Stack. A stack is created at the same time with a thread and is used to store data and partial results that will be required when, say, a method returns its value, and this is where the dynamic binding is performed. Stack can be of a fixed or dynamic size. The stack size can be selected explicitly when it is created. The memory for the stack must not be contiguous. When a method finishes, it is removed from the memory, thereby freeing some space for the new methods. When the stack memory becomes full, Java throws java.lang.stack overflow error. For example, this can happen if we have a recursive function that calls itself and eventually we will run out of memory. Whoever wants to dive into this topic, there is a link in the description that will get you to the right place. So how does this garbage collector actually works? Suppose we have a method called myMethod, inside of which we declare a variable of type calendar. By tradition, we'll call it cal. Since this is a method variable, it does not contain a value until an explicit assignment occurs. And so we assign it a new object of the Gregorian calendar class. And now the variable cal refers to it. But what will happen if we will just set our call variable to null? This will mean that cal is no longer referring to the Gregorian calendar object, and it turns out that actually no one else does. Technically, this makes our Gregorian calendar unreachable for the rest of the code, and since no one else refers to it or interacts with it anyhow, it simply turns into an object floating somewhere in space, taking up the memory. So what happens to such an object? It can probably begin to hear the ominous rustle of the garbage collector from behind his back. This merciless object killer has already started his hunt for the lonely objects that have strayed from the rest of the code. As a reminder, cal is a so-called local variable that exists within the bounds of the my method. That is, the JVM goes through this method, reaches the line with the cal variable, creates a Gregorian calendar object, and in essence give this cal variable a reference link to this newly created object. We can use the cal variable on subsequent lines. For example, we can output its value to the console, but as soon as the method itself ceases, the variable goes out of scope. It stops to be a live, active variable, as if it just freezes in time, sort of. So now nothing refers to the Gregorian calendar object, and our trash friend is slowly but surely begins to creep up to it. But let's go even further and modify our example a little bit. Say we add an outer method that calls my method, which in turn creates a new Gregorian calendar object and assigns it to the cal variable. So now the cal variable refers to the Gregorian calendar object, and we are done here. Then system.out.println prints the content of the cal variable to the console, and the my method returns the cal variable. And when this happens, then the cal variable of the my method goes out of scope and sort of disappears again. But this time my method passes the value of the cal variable to the method that called it, that is outer method. And now, even if the first reference to the Gregorian calendar object ceases to exist, it still won't fall into the clutches of the garbage collector, at least not yet, because there is a new reference from the outer method. Please give this video an emperor's thumbs up, toll the bell and subscribe to the channel. That was V. Thank you, and see you in the next lesson. Thank you and goodbye.